So far, we've seen how to solve some FOLSDEs, but not all FOLSDEs. Which ones? Only the constant coefficient homogeneous FOLSDEs. In order to handle the non-homogeneous and/or the non-constant coefficient case, we're going to adopt an approach that's basically just taking variation of parameters and putting it in vector form. So how does variation of parameters work? First of all, we're only interested in the first order case since we're only solving first order systems here. A general first order equation looks like a of t x prime plus b of t x equals c. You can see a, b, and c here are allowed to depend on t, so this is not homogeneous and it's not constant coefficient. How does variation of parameters work in that case? First, you solve the associated homogeneous system. We're only going to get one solution because this is first order. Then what you do is you make the ansatz that your particular solution should look like x1 times u. You get some condition on u prime, you integrate that condition to find u, and then you just put it together. Remember that because this is a non-homogeneous equation, the solution set will look like solution of the homogeneous problem plus the particular solution. All we have to do with this setup is just translate each one of these statements into a form that makes sense for vectors. Here is that translation. Okay, this theorem is a doozy, so let's go through it step by step and figure out what each part of it means. First of all, we start with our non-homogeneous equation. I've written A here, but you can think of this as A of t. This will work if the coefficient matrix depends on t. The first thing you do is you solve the associated homogeneous problem. Now, if A is an n by n matrix, we're going to get n solutions. Then what you do is you take those solutions and you throw them all into a matrix. This matrix is sometimes called the fundamental matrix of the system. It's a matrix whose columns are solutions of the associated homogeneous problem. Then what we do is we assume that a particular solution can be found by taking that matrix and multiplying it by some unknown vector, u, which means that the operation we're doing when we write x times u is matrix multiplication. If you apply that ansatz, what you find is that your unknown vector u, which depends on t, has to solve this equation. If you differentiate u, which is just given by differentiating each component of u, you're going to get a vector. You feed that vector into the matrix x, and you have to get b out. As we've written this down, maybe it seems tricky to find a u that satisfies that equation. That is, in fact, a first order equation in u, right? It involves u prime. But it only involves u prime, it doesn't involve u, so we can try to integrate. But before we can integrate, we have to get this x off of the left-hand side. How do we do that? We do that by multiplying by x inverse. Once we've done that, we're going to have u prime equals x inverse b. So how do we find u? We just integrate. Use the fundamental theorem of calculus and just integrate. So here's a formula for xp. Namely, you compute the fundamental matrix, you invert the fundamental matrix, you multiply that inverse by b, then you integrate, multiply the whole result by the fundamental matrix again. Now, you can check that this works simply by differentiating everybody. If you differentiate xp, notice xp is a product. Each factor depends on t. If we differentiate the right-hand factor of that product, we apply the fundamental theorem of calculus and just do away with that integral sign. If we differentiate the left factor of xp, we just get x prime times that integral. Of course, x times x inverse is just the identity, so we get b in the first term. And remember that x is nothing more than the matrix of solutions to the equation x prime equals ax. So x as a matrix satisfies the equation x prime equals ax. And then we see that everything but the a, that's just our formula for xp, so the result is b plus axp, which is what we were trying to solve. So this formula will certainly work. The real question is, how do you go about filling out this formula? Let's do an example. Let's start with a constant coefficient example. The first thing we have to do is solve the associated homogeneous problem to find the fundamental matrix x. To do that, we have to find the eigenvalues and eigenvectors of the coefficient matrix, and then our solutions are given by doing e to the eigenvalue times that eigenvector. There you go. We found our two solutions. So what's x? We just throw our solutions into a matrix. We're looking for a multiple u, which should be a vector, u1, u2. That should solve xu prime equals b. Let's go ahead and write down what xu prime equals b means. Now, if you happen to know how to solve that for u1 and u2, be my guest. To me, it looks like that's a coupled system of first-order equations. Doesn't seem like our approach has helped us so far. Let's see if we can apply the formula, though, by inverting x. Inverting x seems like a promising approach because x is a 2 by 2 matrix, and we have a really clean formula for the inverse of a 2 by 2 matrix. Of course, we have to compute the determinant of x. Okay, there we go. There's the inverse of x. And now let's apply our formula. To apply this formula, we just need to multiply x inverse times b. So you can see that this integral won't be the most obvious thing to do, but it's definitely doable if we do a little bit of integration by parts in the second component. Here I've been a little bit sloppy with the constant of integration because I don't actually need a constant of integration. You just need one antiderivative for x inverse b, not to find all of them. And it doesn't really matter where you start integrating. Okay, so that's our u. Our particular solution is nothing more than x times u, so let's go ahead and do that matrix multiplication. There we go, there's our particular solution xp. Notice somewhat conveniently, the exponential functions happen to drop out. This is kind of a big machine we've built and maybe we don't trust it. Let's check. xp is easy enough to differentiate. There's axp, as you might get it immediately after doing the multiplication. Let's clean it up. Having cleaned that up, let's compare it to xp prime. You'll notice that the cosine term in the first component is the same. The sine term isn't. Now let's look at the second component. The sine term is the same. So you can see that this thing definitely does not satisfy the associated homogeneous problem. In fact, what's missing from axp if we want to get back up to xp prime, well, we need to go from minus 8/5 to 32/5 sine 2t. That means that's, what, 40/5 or 8 sine 2t in the first component. And in the second component, we need to get from minus 24/5 up to 16/5. I think we need 40/5, or again, 8 cosine 2t's. And that's exactly right, because 8 sine 2t, 8 cosine 2t was b. Let's write down the general solution, which is just a linear combination of solutions to the associated homogeneous problem plus our particular solution.